Today what we're going to do, so last time we talked about some of the basics of phylogenetic reconstructions. We talked about, actually who can remind me what we talked about? Pop quiz.
How to recover the topology of the genetic tree.
What?
How to recover the topology of the tree.
Yes, exactly. And anyone remember how we did that? Quartet tests, and what was the right metric? Anyone remember who remembered it, who invented it? So there was Steele's metric, which last time we did was we introduced the models on phylogenetic trees, where there's an unknown tree topology and then there are transition matrices on each edge. And what we did was we used the log determinant to actually define a metric. It was first introduced by Steele. And we used that metric, the fact that it's strictly positive, and the fact that we could estimate it to using quartet tests to recover the topology of the tree. So what we have left to do is we want to actually reconstruct the transition matrices themselves once we know the topology of the tree. So this is where tensor decompositions are going to come in, is we're going to use tensor decompositions to find the transition matrices once we have the topology. So first I'm going to talk about that, and then I'm going to show you how the same basic ideas can be applied to HMMs. If you recall, our basic approach in tensor decomposition is we want to be able to take moments of a distribution, which we can estimate, and we want to relate those to three conditionally independent random variables, conditioned on some hidden variable that we don't have access to, but in this case is the state of some sort of node in between. So the basic idea was that the tensors we were going to work with would be things of this form. We would take three leaves, so things that we actually observe A, B, and C, and we would consider some states in our space, I, J, and K, and we would define this to just be the probability that S of A equals I, so the state, this S is this random function, which we described when we introduced phylogenetic models, how we actually construct it. The way we did it was there's some underlying distribution on the root node, and then we propagate it through transition matrices to all the other nodes in the tree, and what we observe is just the leaves. So what we care about is what's the probability that the observed state at A is I, so this is some symbol in our alphabet, and the state at B is J, and the state at C is K. And so the important point is that these three random variables, so these are things that we can measure given many samples from the distribution. We can certainly estimate this quantity on the right-hand side, and we can get progressively better and better approximations to it just by seeing how often in our configuration of samples that this event occurs. Now, one thing I want to tell you about the lesson plan today is we're going to finish phylogenetic trees, but the important point is where the fact that the transition matrices are full rank comes into play. So we're going to crucially rely on that using Generick's algorithm. That was the thing which required the factors to be linearly independent. We're going to talk about how to apply it to phylogenetic trees, but then we're going to talk about one of the classic open problems in learning theory, noisy parity, which we can think of as being very similar to the models that we do have algorithms for, but just where we drop this full rank restriction. So sort of the theme of today is thinking about this full rank restriction. On the one hand, we need it for the phylogenetic trees, for the algorithm I'm about to give to work, and we don't have it in the case of noisy parity, which was what makes it hard. And then what we're going to talk about, or we're also going to talk about perturbation bounds, about what happens when the transition matrices are full rank but are very close to degenerate, how that influences your sample complexity. So that's our lesson plan. But the basic idea is that this tensor now, T, A, B, C, we can actually explicitly write this out as it's just the sum over some hidden states of R, so it's the probability going to do is we're going to choose this node R in such a way that we have disjoint paths between R and A, B, and C. So this way, the crucial point is all we're doing here is this is just the law of total probability. But the important point is when we know the topology and we have these three leaf nodes, A, B, and C, which there is some middle node, which we can find these disjoint paths between, then the important point is if I actually revealed to you what the hidden state of R is, then we would have three conditionally independent samples, because once we've chosen what the state of R is, we just have we just propagate independently across these branches. So that makes sense, right? All right. So now we can write out what this tensor is in a more convenient form. Oops, this is IJK, I guess. So remember that the way that I described this tensor here was I just told you explicitly what the IJK entry is. But now the important thing is what do we think, what does the actual structure of the overall tensor look like? Well, we can think about when we plug in IJ and K here and look at its IJK entry, then what we're really doing is we're plugging in I here, J here, and K here. But the important point is that the structure of this tensor is once we condition on the state of R, then we have these conditionally independent random samples, which are just outer products. Because the probability of getting S of A equals I now is just this product times the probability that S of B equals J conditioned on the hidden state, and similarly for C. So we can write this out now in terms of our transition matrices. So remember that we have these transition matrices from R to A. So we're thinking about the rows in this matrix as representing the different states of R, and then the columns represent the different states of A. So that's explicitly what this matrix is. And then the rows, in fact, sum to 1, just because it's a probability distribution. And what I'm doing is I'm taking the Lth row. So in this way, the Lth row of this matrix is explicitly whatever this distribution is, this conditional distribution of probability of the state of A conditioned on the state of R being L. So in this way, we explicitly have the outer product, and we actually have expressed our tensor that we can estimate as a low-rank decomposition, where the rank is really just the number of possible states.
Anchor?
Yep.
Can I ask you a question?
Yep, please.
So there's one step, no question if I'm following, from the second to the third line.
Yep.
You drop the subscript IJK.
Yep.
I'm not quite sure if I understand that part.
Yeah, so this way, the way that I've defined it here is you give me an I and a J and a K, and you tell me what the probability is that S of A equals I, S of B equals J, S of C equals K. And that's what the entry in this tensor should be at the IJK entry. Now what I'm saying is that, in fact, you can break this up into the probability of S of R equals L, and then you can condition on S of R equals L, but each of those pieces is conditionally dependent. So in fact, this column is just what you get by plugging in different values of I for what actual state you want to observe. So that's the important point. Does that make sense?
So the third line like defines a whole tensor?
Yes.
Okay.
So this third line defines a whole tensor, because the way that you can think about this, right? So this right here is a vector of length, capital sigma, because that's our alphabet, and it's a probability distribution. So the way that you can think about this is, once I choose the state of R, then I'm going to choose the corresponding which entry, which row in this tensor gets occupied based on an independent sample from this distribution. I'm going to choose that as its first coordinate of where I'm going to put something non-zero. The second one I'm going to choose according to this distribution. The third one I'm going to choose according to that distribution. So another way to put it, the way that you can think about this, is imagine there was no hidden state R, and what if A, B, and C really were independent random variables? So then, what is the probability that S of A equals I, S of B equals J, S of C equals K? That would just be the product of those. And that's explicitly what this set of outer products will give you. So that's the way to think about it. Any other questions about this? Okay, so now the key point is that we can apply Generick's algorithm. And remember that Generick's algorithm is really saying that we need that the factors be linearly independent. So in this case, if you think about this matrix PRA, we're looking at the different rows in it. So those are the different factors in this decomposition, so we need them to be linearly independent. So we have is that if PRA, PRB, PRC are full rank, then we can apply Generick's algorithm. And Generick's algorithm in general, so we're thinking of the factors in this tensor decomposition as the rows in this matrix. So remember that Generick's algorithm is only going to recover the factors up to rescalings, but this is actually something which is quite easy to handle here, because we've already fixed the scaling so that the rows sum to 1. So we know uniquely what the right scaling should be, and then we just pull out the missing scaling into this probability term right here. Now the other non-degeneracy of Generick's algorithm is that we can only recover the factors up to permutation, which if you think about it is very natural, because it means that this hidden state, well, we never know which one is L1 and which one's L2, because those two things are the same for us. If we interchange those, we can swap the different rows in all of the transition matrices and preserve the statistical model itself. So the fact that Generick's algorithm only recovers the decomposition up to certain uniqueness really doesn't bother us here, because we know what the normalization should be for these rows, and switching L1 and L2 doesn't change anything anyways. So this was the approach taken by Mossel and Rod. And let me tell you the sort of high-level idea for this, because analyzing it itself is quite messy. Now the idea is, let's see, how do I say this? So imagine that we have some configuration in the tree that looks like this. So imagine there really is an edge between U and V, and then we have some long path between V and W. So you're thinking of this as being some sort of internal edge. So the basic idea is that we can think about a transition matrix, PUW, which transition you apply. So if you have some state for U, how does that affect the state at W? Well, we can think about this explicitly as the product PUV times PVW. Right? So this will allow us to actually, this type of idea, by combining long paths into thinking about them as a single transition matrix, this type of structure will allow us to actually figure out all of the transition matrices in the tree, because now if we go back to our original phylogenetic tree, and let's say we had something that looked like this, well, one of the strategies we can do is we can choose this node to be R. We've already learned the topology. And then we can choose some nodes, A, B, and C. These are explicitly nodes which have 3 disjoint paths. So what it means is that we have some aggregate transition matrix. So even though there's a direct transition from R to A, there's a direct transition from R to B, we have some aggregate transition matrix of R to C, which we get just by multiplying the transition matrix for this edge by the transition matrix for this edge. And then now what we can do is we can observe this configuration of A, B, and C. That gives us our tensor, which we can apply our tensor decomposition algorithm for. And we can recover each of these transitions. But now, how could I try and recover a transition on an internal edge? Does anyone have any ideas? Let me use different colored chalk for this now. So the question makes sense, right? So we've recovered this transition matrix, and this transition matrix, and this aggregate transition matrix. What about recovering some internal transition matrix instead? Yeah.
Just reassign R to focus on the node that's between the current R and C.
Exactly. So instead what we can do is we can plug in R prime here, and then we can find new sets of disjoint paths. And in this way, you can actually pull off what this transition matrix is right here. So if I pull in R prime here, then what are the new paths I'm using? I'm using, for example, these sets. And now I have 3 different leaves, which are conditionally dependent again. So I've created my star diagram. And when I find this path right here, the difference between these 2 paths is just this edge. So when I find this transition matrix and this transition matrix, I can use the fact that the missing transition matrix I'm looking for, this times this equals this, and I can solve for it by a linear system. So this is the basic idea of how do you use muscle and rock, but there are a lot of technicalities to actually getting this result to work. One of the issues is that as you're taking longer and longer paths in the tree, you're multiplying more and more matrices, so the determinant is actually going to 0. So you get less and less confidence about, you have much weaker dependencies, and you need to measure these guys much closer. So that's, yep.
I got a quick question. It's
Yep.
kind of a notational question.
Yep.
Do you mind clarifying the difference between those P's and those P's? Because P, U, W, P, arrow, A.
Yeah. Sorry, that
To
should
the
be
power
same
of
thing.
L.
Yeah.
Sorry, and
Yep.
just to make sure I didn't lose something.
Yeah. So here I'm just adding the arrow notation to make it clearer which one you're starting from and which one you're going to. So you're multiplying, you're left multiplying, which means the rows are U. You're starting with the state of U, and you're figuring out how it can propagate to the states of W. So the important thing is here, that the way that I can do this now is I can think about this guy as being U, this guy as being W, and this guy as being V. So through my 2 different star tests, I'm able to figure out what PU to W is. That's what I get when I try out R prime. And then I'm able to figure out what V to W is. And then I can solve for what PUV is, just by this linear system. So what Mossel and Rock do is they apply this test all over the tree, but there are a lot of complications to thinking about how the dependence on noise works. Because you can think about it intuitively that if I have long paths, then the coupling between this node and this node starts getting worse and worse, and I need much more confidence about those two to figure them out. So I only want to sketch what Mossel and Rock did, but the high-level point is how you can apply tensor decompositions in settings where you have 3 conditionally independent random variables. The other question that I want to get into, which is a sort of important one for you to know, is there are some learning problems which are really not quite so easy. So let me introduce the noisy parity problem, which you can think about as being a similar thing. So let's see. How do I do this? Anyone ever heard of the noisy parity problem? No? So the basic idea is that what we're going to do is we're going to choose a random length n binary string, uniformly at random, so every length n string has the same probability, it's 2 to the minus n. And what's going to happen is that there's some hidden parity on those, on some S nodes. And what we care about is trying to recover this hidden parity. So, the basic idea is that what we're going to then observe is, let me think about a simplified case first. So we choose this X uniformly at random. This is one sample from our model. And what we observe is we just add up all the bits in S, whatever X sub I is, and then we observe what their parity is. So the basic question in noisy parity is what you're going to do is you're going to observe many samples. Actually, this is just the learning parity problem, and I'll get into the noise in a second. So you observe this length n string, and then you observe this parity. And the question is, can you learn the parity from many of these examples? So does anyone have any intuition about this? So is this algorithmically tractable?
Anchor notation question.
Yeah.
So X is just a binary string, and X, what is XS?
Chi-S.
Chi-S, okay. Explain that a little bit.
So chi-S of X, so this is the parity of the S bits in X. So all I'm doing is I'm adding up all of the, X sub I is the ith bit of X. I'm adding them up. And then I'm taking the parity of the aggregate sum.
Okay.
If you want, let's change the notation so that it's clearer on the board. Let's just call it pi. Okay? So pi s is this hidden parity function that we want to learn. So does anyone know how we could try and learn this? Yep.
It's basically a linear system of ref2.
Yes, exactly. So there are actually good algorithms for learning this, because the way to think about it is you're given many of these examples, pair of binary string of length n, and then the corresponding parity. But we can think about it as a linear system. And how do we do that? So we can think about some matrix which each of whose rows is some vector x. Right? So these rows, as we get more and more samples, we're just adding a different row to it. And now what's going to happen So this is, length m because we take m samples, and this is length n because we have length n binary strings. And what's going to happen is that we can think about a 0, 1 vector whose entries are just the non-zeros in S. So whichever, this is a length n vector, and we put a 0 if the corresponding index is out of the set, and we put a 1 if it's in the set. So when you think about multiplying this vector times this matrix, all you're doing is you're adding up the bits in the set S. But the key catch is that you're getting it mod 2, right? So instead, you can think about this as a linear system. And the corresponding entry here would be pi s of x. Because when you multiply these two, but then you do it over GF2, so with modular arithmetic, then all you're going to observe is a 0, 1 value in the output. So the linear system works the same way over GF2 as it does over the reals, that when I generate this random matrix, and I generate its rows independently, very quickly this linear system will have full rank. So I can just apply Gaussian elimination to find what this vector is. So I can solve for whatever this vector is, and then I just create S by figuring out which coordinates are 0 and which ones are non-zero. So a very simple learning problem. Looks easy. It is, but as soon as you add noise to this, it becomes much trickier. So the noisy parity problem now is going to be a slight variant of this, where instead we add some noise term. So the way to think about it is we're still going to get some observation. For every sample X, we're going to get some estimate of what its parity is, but those estimates are sometimes going to be flipped. So instead of actually observing, what the parity is on those S bits, what if instead we add some random noise, which with probability 1/3 flips the answer, because we're working over mod 2. So 1 becomes 0 and 0 becomes 1. And with probability 2/3, it keeps it the same. So this problem makes sense, right? It's the most tame variation on a learning problem. We had learning parity without noise, which we had a very simple algorithm, which just solved the linear system. And then the slightest change to it is adding a little bit of noise, which it turns out makes this problem much, much harder. So let's see how awake you guys are. So first question, so if you understand the definition of noisy parity, is there a sample efficient algorithm? So before, without noise, we clearly had the best of both worlds. We had a sample efficient algorithm. We don't need many rows in this matrix in order for it to be full rank. And we could even computationally find what that set S is. But now what about when I add noise? So is there a efficient sample complexity algorithm? Sorry. Yes, but yeah, that would work. What would maximum likelihood look like here? It will indeed be maximum likelihood, but
I mean, I think it's like a max 2n kind of problem. We try to maximize the number of emissions estimate.
yeah. Wait, was there another yes? But
Given a certain set of samples, you can try all possible choices of S.
yes. So that's the intuition is, imagine you tried out some other S prime here. Well, whatever the true S is, for a typical sample, how often does it agree with the parity on those S bits? It agrees with them 2/3 of the time, because there's a good chance that the noise that you add in is 0, not 1. But the issue is when you have any other parity, its best agreement will only be a half. There'll be some bit that's in one of the parities and not in the other that's just going to make them not agree for half the time. So there's actually a very simple sample-efficient algorithm, but it's computationally inefficient, which is just you brute force search over all of the possible hypotheses. So let me make this more precise. So there is a simple sample-efficient algorithm, and here's the approach. So all you do is you have your function that you have access to. You take random samples from X, and then you ask how long, how often is the output that you get from noisy parity. So it's not just the parity on S, but it adds in the noise as well. How often does that agree with what the parity on T should be? Okay. And the claim is so here's the idea. So it's clear that if T equals S, then the probability is 2/3, right? Because when I add in 0 noise, they're definitely the same answer. I haven't added any noise to it. Now, if you think about, what T is and what S is, there's a simple case that can sort of convince you of this. Imagine that S is the first few bits, the first K bits in the string, and then T is just a bit larger, adds in one more bit. So the way to think about it is that S doesn't depend on any of this last bit right here. So once you choose what this is and you choose what the noise is, well, you still have a 50-50 shot of flipping the value of T. So it only has a 50-50 shot of agreeing with whatever that is. So that's the basic idea. And what you can do is you can take the same set of samples and just compute all of these different probabilities. And what this gives you is it gives you something like n log n samples. So this is a great case for, the noise doesn't actually change the sample complexity, but it turns out is it drastically affects the computational complexity. So this algorithm runs in 2 to the n time, right? So are there any guesses about what the best algorithms we know, the state of the art in theory is for this particular problem? It's kind of embarrassing, but instead of 2 to the n, I run in 2 to the n over log n. So after all this theory work, what we can do is we can put an extra log n and divide by log n in the exponent. So in fact, people have started basing crypto schemes on this particular hard problem. But what I want to show you is that, so this problem, just adding this simple bit of noise, we can actually think about it as fitting into our model for phylogenetic trees and so on, but just in the case where the transition matrices are not full rank. So that'll be the killer. So in fact, once you move beyond this full rank condition, things really do go out the window, and you start ending up with problems whose best sample complexity is still polynomial, but which we have no efficient algorithms for actually matching roughly, poly runtime.
But
I seem sleepy today, so ask me questions. Yeah.
do we have hardness results on this? So we're not yet.
No, because so this is an average case problem. So it's difficult to come up with hardness results for these things. It's the same reason that in crypto, you can't really base public key encryption on worst case hardness. So these are just the types of problems which are conjectured to be hard. Actually, I hear that the NSA actually relies on this problem being hard as well. So there's some good evidence. Jim Simon said something like that. Any other questions about this? Yeah.
This is just is it reasonable to think of this as a very special case of the general working with errors framework?
Yes. Yeah. So there are even further generalizations where instead of working with mod 2, you can work mod something else. And then those problems are also used in cryptography. So I think this is the crispest version of it, at least from a learning standpoint. But there are other variants of this that also have the same gap, that information theoretically you can do with few samples, but computationally we don't know very much that's non-trivial. So a lot of things like homomorphic encryption are based on exactly this type of problem. But let's think about it now, this noisy parity problem, as an instance that fits in our stochastic models on graphs framework. So let's imagine that we have a length 4 parity problem, noisy parity. What I want to do is I want to define a stochastic model that just so happens to output whatever noisy parity would output to. So the idea is that we have these 4 output bits. So that's our random sample that we want to observe. And we're going to say that x1 shows up here, x2 shows up here, x3 here, and x4 here. So these are just the bits in our random length n string. We're going to observe them here. Now the key point is that in each of these nodes right here, we're going to keep track of what bit we want to output along with the running parity so far. So in this case, it'll just be, put it this way. So for example, if we have stored at this bit right here, so what we're going to do is we're going to lazily generate what the bits are in our random string. So imagine we generate the first bit. We choose x1 to be randomly, 1 or 0. And then what we can do is we can keep track of the running parity on all the bits we've generated so far. So if, for example, if the first index is in the set S, so x1 contributes to the parity on S, then what we're going to do is we're going to put in x1 in that location. If x1 is 1, that's our current running parity. If x1 is 0, that's our current running parity. Now, if 1 is not in S, we're just going to output 0 and ignore everything, right? Because it doesn't contribute to the parity. So in this way, what we can do is for the second state, we can think about, we want to generate x2, and what we're going to do is we're going to look at the sum from all I in S, I from 1 to 2 of xi mod 2. That's the basic idea. So if both 1 and 2 are in our set, we're just going to take what the parity is on those bits. If one is in 1 and the other isn't, we're just going to put whatever that bit is. So we're just keeping track of the running parity as we go along. Now the important point is that we can actually think about these as transition matrices now. So if I think about the transition matrix between I plus 1 and I, so let's say that the state at the ith node is some xi and si pair, right? So this is the ith bit that we've generated. This is our running parity up to the ith bit. And what we're going to do is with probability 1/2, we're going to choose that the next bit is 0, in which case we don't update our parity no matter what. And with probability 1/2, so if I happens to be in S, actually let me phrase it this way. So imagine we're in the case where I belongs in S, and we have our current bit, I plus 1 belongs in S. And we have our current bit I, and we have our running parity total, Si. Well, if the next bit is in S, what we're going to do is there's a 50% chance we generate the next bit to be 0 anyways, in which case we don't update the running parity. There's a 50% chance that we choose the next bit to be 1, in which case we do update the parity because I plus 1 belongs in S. And otherwise we keep it the same, right? So the same thing, and we can do the same thing when I plus 1 is not in S, so let me write out what that is. So in the case where I plus 1 isn't in the S set, then it's not going to influence our parity. So all we do is we generate whatever the next bit should be 50-50, 50% chance it's 0, 50% chance it's 1, and then we keep the running parity the same. So in this way, as we go along our sequence, we're just generating what the next bit should be that we're going to output, and then we're updating our running parity as we're going along. So in this way, then, we can actually propagate whatever, our matrix that transitions from here to here is just going to keep only what the first bit is, because that's the bit that we've lazily generated. And at the end of the day, this last transition, it's just going to add noise. So in this way, the way to think about it is that this is a classic, learning problem now, which you can just think about as generating observations from this stochastic model. But the key is that you don't know the transition matrices. So why don't I know the transition matrices?
We don't know S.
We don't know S, right? So we know this caterpillar-like structure. In fact, we even know what this thing is right here, because let's say you know that there's a third probability you're going to flip the bit. But the key point is that the domain of this hidden state is size 4 now, because I have 4 possibilities for what the bit is, the x of I that I just generated, and what the running parity is. That's what it needs to keep as I'm going along. But all I generate in these observations is just a single bit. So my hidden states are size 4, my observed states are size 2, so there's no way that this transition matrix can be full rank. And that's exactly what goes wrong for noisy parity. You can think about it as we can't apply generic in this case, but it's a more serious issue that we don't even believe that there are efficient algorithms for this problem, and crypto is based on this. So you have to be careful with the full rank type of condition. It really is a very strong one. And there's some cases where it's legitimately not the right thing to do. Does this make sense? Yep.
Can't the transition matrices be made full rank without giving out the information about S?
Without giving, so do you have a proposal for how one might do that?
Like just add once, like this has to make full rank, but it might not mean anything.
So I mean, it's tricky because the natural thing here is if you want to keep in your state just the running parity, then the next step, what you have to do is you have to simultaneously generate what the next bit is going to be and update the new parity, and you want to output both of those. But then you would have the issue that the natural way of trying to do that would have sort of coupled transition matrices here. Because the way, whatever next bit I output, which is my next bit in my parity, in my observation, that would influence how you update the parity or not. So in that case, they wouldn't actually be conditionally dependent on this random thing. But more qualitatively, if you could do that, you could solve noisy parity. And then you would break all of this, modern crypto that's based on things like this. All right. So what I want to do now is I want to move on to perturbation bounds, but I think it makes sense to take a short break if you guys have more questions about this. Yeah?
Not in this particular model, but in general, is there anything we can observe about just the output of this sort of model that would tell us whether transition matrices are full rank or not? If we don't yet know anything about the topology of our tree.
Right. I mean, one thing you can do is you could always just assume that it is, let's say you knew the topology. You could assume that it is full rank, learn, your model, in which case your model would be statistically close to the right answer because the transition matrices are full rank and you have the benefit of generic. But in the case where they weren't, what you learned then either is statistically close and you can just forget about the original model and there is one that has full rank. Otherwise you can't and you would know it because statistically you wouldn't be able to couple the distributions that way. So yes and no, but that's a good question. I don't know of anything smarter than that actually. Yep.
Can you explain again why it is not full rank?
Why it's not full rank. So remember that this is, the natural way to think about this is that this is actually a hidden Markov model. So we have these hidden states, and we have these observed states right here, which we get to get. So this right here is just, pi s of x, with noise in it. And what's going on is it's a very, all of the tools you develop for, phylogenetic reconstruction work for hidden Markov models too. So you can imagine that if all of these transition matrices were full rank, one of the things I can do is I can choose my root node R to be here, and then I would get 3 conditionally independent random variables, which then I could use to find this aggregate matrix, and this aggregate matrix. So in fact, HMMs are really just the special case of phylogenetic trees if you think about them the right way. But the issue is that in that same model where you have this hidden state going along generating observations, if I engineer it the right way, I can construct one that creates noisy parity. And the way that it's going to do it is we definitely have to generate our random length 4-bit string, which we're going to do because each of these states is going to tell us what we should output. So the first state is going to come hand in hand with x1, which is the first random bit, but it's also going to keep track of what it needs to do at the end. So to that end, what it's going to do is it's going to keep track of the running parity. It can't keep track of the whole parity because we haven't even generated those bits yet. But the issue is that this hidden state now is a length 2 vector with binary values. So it's 0 and 1 because we have 2 choices for, for example, what x2 is. And we have 2 choices for what this parity, the running parity is right now. So that means we have 4 states for this hidden node, but all we output here is actually a state which has 2 values. It's either 0 or 1 for our observation. So the issue is that we have 4 states here, and we only observe 2 states, so there's no way that that transition matrix can be full rank. So that's the issue. It's just the simple 4 versus 2 issue.
But transition matrix means the transition of the hidden state.
Also the observation matrix. So the observation matrix is the thing which is going from 4 to 2. So, this matrix is the culprit.
But that's not a huge problem, right?
I don't know. Can you solve noisy parity?
No. But usually the problematic thing is the rank deficiency of the real transition matrix of the hidden state.
Of these things,
yeah.
right?
Yeah, here is the transition matrix of the hidden states for rank.
No. So, let's see. Well, so it's this transition matrix right here just has 2 non-zero values. It's a 4 by 4 matrix because we have 4 states for the starting and 4 states for the ending, but it only has 2 non-zero values. So you also have the issue there because I just have half and half.
It's rank 2?
It's rank 2, yeah. Anyways, let me take that one offline. But all right, let's take a short pause before I go on to perturbation bounds. So the latter part that I want to cover today is, so we're really thinking about, in the case of phylogenetic trees, if you have full rank and you exactly observed these tensors, you'd be in great shape. And the case where full rank is violated, even if you exactly observe things, you're going to have issues. And now what's going to happen is we're going to ask what happens when we're close to low rank, but we just have samples and we only get noisy approximations to our tensors. So we're going to start to work with issues like, when are these algorithms actually noise tolerant to recovering the true transition matrices or something close to it? But let me give you guys a breather so you can ask me more questions. So we'll take a 5-minute break and then resume.
I broke it. Goodbye. Put all my money into it. Always fast. Finish my homework slightly late, and it might be on Thursday evening.
All right. Yeah. Yeah.
Okay. Do you need a copy or?
Yeah. Oh wait, you emailed it, correct?
Yes.
Then I have it.
Okay. I also have a question about that.
Yep.
Does this problem become easier if you can choose your samples?
Yes. That's a good question.
Okay.
Yes.
So, how fast can we solve it if we
Polytime.
and
Yeah.
polytime?
Yeah. So the way to think about it is, if I want to determine whether a bit is an S or not, I can definitely do that. Because one of the samples I can choose will be all zeros and just 1 1 at that location.
Oh, and then you average multiply.
And then I do it many times and I average. So if you think about it, adding noise if I get to ask questions really doesn't change anything.
Yeah.
Because I'll just ask the same question so often that I know the answer.
Okay.
And then you can solve it. Yeah. But that's a good question. Yes. Yes. Oh, okay. Yep.
I also have a question about following one party notes, but I can't remember my
Okay.
All right. Flaws the size of that.
Yep.
But what I was saying is that the observation loses ranking because that we can always stack into
Because it's always
Yeah.
to do generate
You're saying, you know, so if I.
Not in this case,
Yeah.
but in general, you have ranking observation.
Yes. Yes, but not in this case. Definitely not in this case, right?
So usually, but usually when the transition is
Yeah.
generate values doesn't have at all.
Yes, I agree. But even here, I mean, there are some.
I guess if you have like if you stack more instead of doing 4, then you have like 5 or 6.
Yep.
And if you have a full transition, even if what you observe is only the current generation, you will still be able to move.
Not for this problem, though.
Even if you have more than 4 stages.
For noisy parity? I mean, I hope you can. This really is hard.
Okay, well the hardest because of the transition matrix.
Well, it could be the observation matrices. I'm not sure the observation matrices cut through route in the way you want them to, but I have to think about that one. But it's definitely going to go wrong here. Otherwise, we have different issues on our hands. This would break, for example, fully homomorphic encryption, if we could do that. So that'll be bad, because I think DARPA has a few $1 million on it. I don't know, $100 million on it or something. All right, so any other lingering questions about this? This is an important one to keep in mind. Just because you can learn some hidden Markov models doesn't mean the world is your oyster and you can do whatever you want. You still have to worry about what cryptographers tell you can't do. So don't accidentally do this unless you really want to. That's my point. You know, the other thing I want to do is I want to make some of our discussions a little bit more precise, because you know, this is something which is always a pain to do. That you know, everything we did in Generics algorithm, for example, Generics algorithm, we've now seen a bunch of different applications. We applied it to topic modeling, that was Ron's lecture. Then we applied it to phylogenetic reconstruction, and we applied it to HMMs. And the key idea is always, where do you get your conditionally independent random variables? Because that's what ensures that the tensor you observe has a low rank structure. And then when you can decompose it, you learn something about the parameters of your model. But now there's a big issue there, which is that we didn't talk about what happens when Generics algorithm is given a noisy approximation of the tensor. So if you think about your tensor as coming from third order moments, that's something which you can estimate as finely as you want. You know, if you want a really fine approximation, you take tons of samples, and then you take your empirical average, and that's good enough. But you can never hope for an exact value for what that tensor decomposition, for what that true tensor is. So we should really care about when Generick's algorithm is, what are the conditions under which it's robust to noise? Because the way I've been describing these algorithms is you're given exact access to various things. And to get the full theorem statement, you would really care about what the sample complexity is, and then how close you're guaranteed to be to the true answers. So all of that is hidden here. And for one time, we're going to do the messy perturbation bounds. But this is just meant to convince you that I'm not cheating when I really resort to thinking about given exact access to things. Because what you'd really do is you would rely on these perturbation bounds to get precise theorem statements. So anyone remember what's the workhorse in Generick's algorithm? So is eigendecomposition, right? Is what we actually did was we took two different flattenings of the tensor, and then we took one matrix times the pseudo-inverse of the other, and we looked for the eigenvalues and the eigenvectors. That gave us the factors in our decomposition. So really building up towards for perturbation bounds, is we want to answer the question, when is an eigendecomposition robust to noise? That's the key point. That's the key question. So we're going to start with much simpler questions. We're going to start with the question, when is solving a linear system? So an eigendecomposition is really just a collection of linear systems. So the first question is, when is solving a linear system robust to noise? So the way to think about this is, what if we have some linear system, mx equals b, but instead of b, what we're actually given is we look for a solution to some related linear system. So here we're in the setup, which is a little bit different than the way that we're going to apply it to eigendecompositions. Is what if we have perfect knowledge of this linear system M? We know exactly what the constraint matrix is. But what happens if what I really wanted to solve was this true linear system, mx equals b, but I don't actually get access to the right-hand side. Instead, what I get is b tilde, which is off by some additive error term. So what we care about is, how does our error in our observations translate into errors in the things we want to solve for? So the way to think about this is, what if the right-hand side come from observations from some stochastic model? These are things which we can drive down to zero at some inverse polynomial rate as we take more and more samples. But what we care about is, when does that actually drive the error in our estimates of our parameters also down at some good rate? So we care about what's the relationship between these two. So in fact, one of the crucial definitions, this is sort of the basics of numerical analysis that we'll need, is the key definition is what's called the condition number. Which the thing that you should remember, which is the takeaway, is that it's the condition number which governs the stability of a linear system. It has a very simple description, especially once you've introduced singular values. But it's just the ratio of the max to the min singular value. That's the condition number. So what's a perfectly conditioned matrix? What's a condition number with as small as possible condition number? Yep, and what are some matrices that would have that? The identity and orthogonal matrix. So these are linear systems which have as good behavior in terms of how the error in their constraints propagates to error in their true value. You know, if you had the identity matrix or you had some orthogonal matrix, when I multiply by M inverse, all I'm going to do is whatever the magnitude of my error is, that'll be the magnitude of my error in what I find for x versus x tilde. But in general, it'll be the condition number that governs that relative change. So let's see why that is. It's a simple exercise, but it's a very enlightening one to do. So let's solve for x tilde. It's just M inverse times B tilde. So pop quiz, why do I know M is invertible? If I have a bound on the condition number?
Because you were able to calculate it.
Yeah, otherwise it would be infinity, right? So in the case where where it's not full rank, then condition number isn't going to give you any bound. But in the case where you do have a bound on the condition number, it'll show you how much the errors blow up. So I'm going to multiply by M inverse. And now all this is it's just M inverse times B plus E, which we get x plus M inverse times E. So now what we're going to do is we really care about the magnitude of E is really the difference between B and B tilde. That's the norm of that. And what we care about is how that influences the norm of our estimate to the true thing. So we actually care about is the norm of x minus x tilde. So how can I bound this based on the norm of E? How large can this be?
The minimum singular value of
Exactly. Because M inverse, all we're doing is we're taking the same SVD of it, but the singular values become their own reciprocal. So sigma max was the max value that you can blow up, the norm of a vector. That's when we talked about the operator norm at the very beginning of class. And the same way when you talk about how large M inverse can blow up the norm of a vector, the worst it can do is 1 over sigma min. Right? And the last step that we're going to need is that we know that mx equals b. So by a similar chain of reasoning, we have that the norm of b itself is bounded by sigma max times the norm of x. Because that's how large you can blow up the norm of x to get the norm of b to be. Now these two things are actually going to, couple together, are going to give us our bounds we care about. Because what we really care about So now I can get an upper bound. If I care about this quantity, all I'm going to do is I'm going to substitute something smaller in the denominator, which in this case is going to be the norm of b divided by sigma max. And in that case, what I get is I get norm of b over sigma max times sigma min, because I had that right there, times b minus b tilde. So I'm just plugging it in. And lo and behold, what I get is I get the condition number of M over the relative error in B. So the way to think about this is I care about the relative error, so the ratio of the difference in x versus x tilde, compared to the norm of x itself, because that's what it's fair to compare against. That's the norm of the thing I'm looking for. And that in general is bounded by the condition number times the relative error in B. So this is the way to think about it, is that, of course I'm in great shape when I have things with condition number being 1. When I have things like the identity matrix and orthonormal matrices. But in general, this right-hand side is something that we get to control, because as we take more and more samples, we get tighter and tighter approximations to the constraints on some linear system. You should think about that as we get tighter and tighter values, bounds on the values in some tensor. So as we can drive this quantity to 0 as we take a polynomial number of samples, the key point is that as soon as you have some polynomial bound on the condition number, that's when you get efficient algorithms. Because then by virtue of driving the relative error at B to 0, you can drive the relative error in x to 0 at a good rate. It's just when you have any bound, any reasonable bound on the condition number. So that's the first thing to think about, is this is working our way up towards when eigendecompositions are robust. It's just understanding when linear systems are robust. So the remaining result, which I want to do today before we prove the full statement, is I want to prove one other theorem, which is really useful now. These two theorems together are going to be what give us our results about perturbation bounds that we'll need. So the remaining theorem is Gershgorin's disk theorem. So anyone heard of that? One, sort of? Okay. So and the way that you should think about this is it's going to be stated a little bit differently, but you should think about it as when you have control over small perturbations, not influencing eigenvalues. So we're going to use things like perturbation bounds for linear systems to control that the eigenvectors are not changed that much. But we also need some tool for controlling the eigenvalues. So the way to think about this is, what if we were in the simplified case where we started off with a matrix which was the identity matrix? And we cared about was, when we can create small perturbations to that identity matrix to still have roughly the same eigenvalues. So Gershgorin's disk theorem is something which is going to immediately give us that, but let me tell you the precise statement of it. So let's say, we have some matrix M that we're interested in. So the main result is actually that the eigenvalues of some matrix M are all contained in the following collection of objects. The collection of this union of disks. So what we're going to do is we're going to take a disk which is centered at one of the diagonal entries, so I comma I, and we're going to look at some disk of some radius Ri, where Ri is the sum of the absolute values in that row. So, if you think about it, if you had a diagonal matrix, right? What are the eigenvalues of the diagonal matrix? They're just exactly along the diagonal. And then in that case, if I take the entry along the diagonal, this radius is going to be 0 because there are only zeros along that row. And so what we then are saying is that the eigenvalues are contained in these 0 radius disks at each of the diagonals, which recovers a result that we already know to be true, that the eigenvalues of a diagonal matrix are themselves the entries along the diagonal. So that's a good start. Just to be more precise, D of AB is just the set of all x's where the norm of x minus a is at most b. So the way to interpret this is it's the disk centered at a of radius b. And we've already said that this theorem is going to recover one fact we already know to be true, but it's going to tell us even more than that, because when you have a near diagonal matrix, imagine, we know the eigenvalues of a diagonal matrix are just the values along the diagonal. Now what happens when I add really, really tiny perturbations, 1 over n to the 100, to each of the entries in that matrix? Intuitively, you hope that it doesn't really change the eigenvalues. That's the point, right? And so let's prove this. This is actually pretty easy to prove. Surprisingly powerful statement. I'm surprised they don't prove it in linear algebra classes, but it's cool. And there's one crucial trick. So, how else are you going to prove this? You start with some eigenvector, eigenvalue pair, and you prove that, lo and behold, it is in one of these disks. But the question is, which of these disks should we put it in? So there's one trick in Gershgorin's theorem, which is the following. So you give me an x and a lambda that you say is an eigenvector, eigenvalue pair. What I'm going to do is I'm going to let I be the arg max over j of the absolute value. So I'm just going to choose I to be the index with the largest magnitude value in it. So you give me some eigenvector, and then I look at it and I tell you I, which is the entry of largest value. In the case where there's no strictly largest, you could choose I to be any of the ones, which achieves the maximum. That doesn't change anything. But now the key idea is we're going to use the fact that it's an eigenvalue, obviously. So it satisfies this condition. And what we're going to do is we're going to look at the ith row of this linear system. So we have this linear system which satisfies this condition. And we get out just by looking at the ith row is that the sum over j of mij xj is equal to lambda times xi. Just pulling out the ith row, nothing complicated. And now what I'm going to do is I'm actually going to pull out the ith entry, because that's the center of the disk that we care about. So I'm going to take all the other things and keep them over here. Okay? And now we're almost done, because all we're going to do is we're going to take the absolute value and divide through by xi, which is the largest magnitude entry. So we have now that lambda minus mii is equal to absolute value of sum over j not equal to I, mij xj over xi, which lo and behold is equal to this radius ri. So why is this true? Because we chose xi to be the largest magnitude thing. So I could just apply triangle inequality and then replace each of these with 1, because that's an upper bound for it. And lo and behold, I get this radius. So this tells me that lambda minus mii is in this disk of radius ri. Now, one thing to be cautious about is that this is a disk in the complex plane. It's not a disk in R. So in general, I certainly could take a real valued matrix, add some small perturbations, and push some of the eigenvalues up into the complex plane, just not too far, because if it's a small perturbation, I can only move them so far off of where their original center was supposed to be. So that's the key point. And the last thing that I want to say is that there's actually a stronger version of Grishkorin's theorem, which I'm not going to prove, but it turns out when the disks are disjoint, then each one contains one and only one eigenvalue. So the way to think about this is, what if I gave you a diagonal matrix whose diagonals were distinct? And then if I have a small enough perturbation so that around each of those diagonal entries, those disks are disjoint. So there's an important caveat that the way that I prove this theorem, all it's saying is that the eigenvalues are contained in that union of disks, but they don't a priori tell me that one disk could contain two eigenvalues. Because this was just a proof by contradiction. You give me an eigenvalue, and then I tell you one of the disks it belongs to. But actually, there's a stronger version of this theorem that actually says when the disks are disjoint, that it actually behaves like you would expect it. And actually, the intuition for this proof is very crisp, because what you can do is, if you think about that diagonal matrix with distinct entries along the diagonal, and you think about the perturbation you're adding to it, what if I think about slowly adding that perturbation in? So I'm scaling it down by something small. When I initially add in no perturbation, we know exactly where the eigenvalues are. And then I'm slowly deforming these regions, these disks which contain those different eigenvalues, but an eigenvalue can't skip from one to the other. That's just the continuity properties of eigenvalues. So it actually tells you nice things like this. So what we're going to use this for is, remember in Generick's algorithm, we needed properties that the eigendecomposition is unique, and we're also going to need that it's robust. So at the end of the day, the question that we're working up towards is for this question, where we're asking, when is the eigendecomposition robust to noise? It'll be under two conditions. When the eigenvalues are distinct, enough that they're non-negligibly different from each other, and when the condition number of the diagonalizing matrix is reasonably bounded. Those are actually the only two conditions you need to prove bounds on how robust the eigendecomposition is to noise, and you can derive bounds based on those two quantities. So we saw right now is just the two isolated pieces, the condition number and how it controls relative error, and the Grishkorin's theorem and how it depends on the distinctness of the roots in order to imply that each disk contains one and only one. We're going to put them together to prove our perturbation bounds. So that's the basic idea. All right, so I'll stop here and take any questions you guys have.
Ankur, could you raise a proof
Yes.
from the depths of?
Such a short proof. Actually, that's not true. I can give you an example where it's not true, but it takes a little bit of work. Yeah, so you're asking, let me simplify the you're asking if I can change my definition of radius to, instead of being the L1 sum of the off diagonals, to being the L2 sum. Let's say. Yeah, actually, it turns out to not be true. But it's not obvious to construct the example. I can show you, I can tell you an example of this. So imagine I take a matrix which has two n columns and rows. And what I'm going to do is I'm going to put the identity matrix here, and I'm going to put the Fourier transform matrix here, like the DFT matrix. So if I let this be my matrix M, then what I can do is I can do M transpose M. Right? What I claim is it has ones along the diagonal. It's a 2n by 2n matrix, where all of these entries are magnitude at the most, right, 1 over root n. Now, Gershgorin's theorem is going to tell you when a submatrix of this is full rank. So Gershgorin's theorem tells you that if I choose at most roughly root n rows and columns, and look at the submatrix, that it should at least be full rank, because none of those disks hit the origin. So imagine I take root n over 2 columns, and I take the corresponding rows. So then when I look at just that submatrix that I construct, you know, root n over 2 by root n over 2, then my radius value here is, you know, half.
Exactly. Yeah.
Right? So you would think, so Gershgorin's theorem tells you that it's fine that this is full rank matrix, right? But it actually turns out, so if you had an L2 version of the radius, you would be able to go out to linear.
Exactly.
Right?
Yeah.
That's not true because the following example. So if I take the column function, so, you know, separated points, which are root n apart, it's its own Fourier transform. So that actually, what it tells you is it tells you an explicit, you know, roughly root n by root n, you know, like 2 root n or something, submatrix, which is not even full rank. So in fact, that's a good thought. I've thought that before, but it's false for this reason.
So we cannot change it, like there is no extension of this thing.
Not that I know of. I mean, the most natural one would be L2. L2 definitely fails for this reason, because you can't even define the radii in a sort of non-trivial way based on that. I mean, I guess unless you scale them up by like a root n or something. But I don't know of any other versions of Gershgorin, and L2 is false in the natural
And
way.
this has application in random matrix theory, right?
Has applications everywhere. Everywhere.
Yeah.
I mean, it's everywhere. I'm actually always shocked that no one knows the
I
proof
think
of
I've
it.
heard about it in the random theory. I didn't know the name.
Yeah,
actually.
what I don't like is that a lot of times when people discuss this, they make it out to be some like deep theorem. It's not though.
Yeah.
It's really not.
Yeah, the proof was kind of trivial. I asked for an extension of
Oh,
the
yeah.
problem set.
Right,
Thanks a
because you
lot. And
added
I
late,
added the
right?
course.
Yep.
Yeah. Thanks a lot.
Yep.